Many people struggle with fully utilizing MQTT for building connected solutions. So in this video, I'll break down exactly how you can leverage MQTT to build robust connected systems. We'll start with the key MQTT principles that enable scalable and resilient architectures, and then we'll dive into advanced MQTT features that ensure messaging reliability. Now, having worked with engineers and architects across various industries for many years, I've seen the same patterns of confusion and missed opportunities when it comes to MQTT. My name is Kudzai Manditereza with Industry4.TV. I regularly publish industrial Internet of Things tutorials on this channel. So if you find this content helpful, be sure to subscribe so you don't miss any of the upcoming videos. Now, to effectively build connected solutions using the MQTT communication protocol, it's crucial to first understand its communication architecture. MQTT uses a publish-subscribe mechanism for exchanging information, and the best way really to explain how that works is to examine how it differs from traditional methods of connecting devices and machines to the internet like HTTP. In HTTP communication, there are two main participants, a client and a server. These two are directly connected. When the client needs information, it sends a request to the server, which replies with a corresponding response. This exchange happens synchronously, meaning the client waits for the server's reply before proceeding. In contrast, MQTT does not involve a direct connection between the two participants. Instead, a third component is introduced into the network, which essentially acts as a server. Its role is to coordinate the exchange of messages between the two participants, both of which function as clients. In MQTT, the client serves as the information source and pushes data to a server known as the MQTT broker. The broker then coordinates the distribution of the data to any client that needs it. This decoupling allows you to add more participants to your network, whereby each participating client is able to both send and receive information through the central MQTT broker. Now, it might seem unnecessary to introduce a middleman between communicating entities. However, this approach becomes clearly beneficial when considering the flexibility, efficiency, and scalability required for message exchange among hundreds, thousands, or even millions of participants in enterprise applications. Let's explore some examples to illustrate this point. Imagine you have a predictive analytics application that is directly connected to assets such as an assembly robot, a compressor, and an automated guided vehicle on the factory floor. Using HTTP's request-response model, the application needs to continuously send message requests at a specified frequency, say every second, to achieve near real-time reporting of events and up-to-date status of the assets. Now, if you have 1,000 such devices, you would be sending requests 1,000 times every second. This approach has significant drawbacks, including computational costs that escalate quickly as you increase the update frequency or add more devices to your network, along with the subsequent increase in network load. Now, what MQTT does by introducing a broker between the connected devices and your application is allow clients to send, or rather publish, information to the broker only when they deem it necessary or when an event occurs. Because the application has already notified the broker about the information it is interested in or subscribed to, the broker will relay that information to the application. Later on in this video, we will discuss in detail how the actual process of publishing and subscribing to the broker works. But for now, I want us to focus on how the components function in this architecture. Essentially, the MQTT publish-subscribe approach provides an architectural framework for building event-driven solutions where applications and devices respond to events as they occur, making it ideal for reactive applications that require real-time processing. By reacting only when changes occur, systems can be more efficient in their resource usage as opposed to the polling mechanism that requires constant resource allocation. Subscribers only receive relevant data, reducing network load and processing demands. Moreover, unlike the request-response model in HTTP, where both the client and the server must be online and available simultaneously to exchange information, the MQTT publish-subscribe model operates differently. For instance, suppose your predictive analytics application experiences a failure. In that case, The asynchronous nature of MQTT's publish-subscribe mechanism allows the system to keep functioning by queuing messages from the devices in the broker. These messages will be processed once the application's service is restored. Again, we will discuss the details of how this works in a later section. Now, suppose you decide to introduce another application, such as one for energy efficiency. Using the request-response approach, you would need to create a new set of direct connections to the devices on the factory floor. If you require information from yet another source for context, you would establish another direct API connection. As you can see, this begins to create a complex network of tightly coupled connections, where applications depend on the SDK or API configurations of specific devices and applications they are connected to. This complexity increases exponentially as you add more participants to your network, making it difficult to manage and scale your solution. By introducing an MQTT broker to coordinate communication between clients, you effectively decouple the components and eliminate one-to-one relationships between your devices and applications, replacing them with one-to-many and many-to-one relationships. This allows you to create a decoupled communication network where publishers and subscribers operate independently and do not need to know anything about each other's implementation details. Changes to one component do not affect the entire system, providing flexibility and scalability. Components can be scaled independently, updated, replaced, or added without necessitating changes or downtime in other parts of the system. In fact, you can continue adding clients up to tens of millions of connections. However, as you increase the number of MQTT clients to such large scales, the volume of messages and the number of concurrent connections also increases. This poses the risk of sacrificing performance or reliability of the central component, the MQTT broker. To address this issue, the MQTT publish-subscribe architecture allows you to increase the capacity of your system by adding more message broker instances to handle the increased load without needing to modify the architecture or other services. This horizontal scalability is critical for supporting the dynamic workloads typical in enterprise IoT applications, large-scale messaging systems, and any scenario where real-time data distribution is crucial. One common approach to achieve horizontal scalability in MQTT is through broker clustering. A cluster consists of multiple MQTT brokers working together as a single logical broker. This setup can handle more connections and messages than a single broker can. The brokers in a cluster share the workload and in some configurations can also provide high availability and failover capabilities. Now, this should give you a basic understanding of how the MQTT publish-subscribe architecture functions. However, it doesn't explain exactly what form of addressing MQTT clients use to share and access the data they need from the broker. In other words, how does the MQTT broker determine the distribution of messages to clients? Let's explore that next. To recap, MQTT communication involves three components: publishers, subscribers, and a broker. Publishers send messages, subscribers receive them, and the broker acts as a central server managing the distribution of the messages. An MQTT client can function as both a publisher and a subscriber. Now, to help the broker determine which recipients should receive a specific message, the publisher includes a string identifier called a topic along with the message. For example, a client might publish the vibration measurements of a compressor to the broker under the topic compressor vibration. Any client interested in receiving the compressor's vibration readings each time they are published to the broker needs to subscribe to the compressor vibration topic. This, of course, means the subscriber must know beforehand which specific topics to subscribe to in order to receive the published messages. Now, here's where it gets interesting. MQTT topics are structured hierarchically using forward slashes to separate different levels. For example, the topic for publishing the compressor's vibration could be structured as factory/compressor/vibration. Now, this is a feature that I believe is really underappreciated because it elevates MQTT from being merely a protocol for moving data from point A to point B to one that allows you to design structured data access across devices and applications in your MQTT network. For example, to provide subscribers with granular access to data about the components of a compressor, an MQTT client could publish the motor's temperature and current readings under these topics. Similarly, the temperature and flow rate readings of its cooling system could be published under these topics. Meanwhile, an analytics application consuming all this data from the factory to generate predictions could publish prediction results under a dedicated topic. Any application or system interested in these results can subscribe to receive them through the broker. Now, it doesn't end there. MQTT allows subscribers to use wildcards to receive messages from multiple topics at once. And there are two types of wildcards. The single level wildcard, a plus sign, which can substitute for one topic level. For example, if the analytics application wants to receive temperature readings from all components of the compressor, it can use the plus wildcard in its subscription as shown. Now, this would match these topics. There is also the multi-level wildcard, a hash sign, which can substitute for any number of levels. For example, if the analytics application wants to receive all sensor readings from all components of the compressor, it can use the hash wildcard as shown. This would match all topics that start with factory/compressor. And to receive all sensor readings from the factory, it can use the hash wildcard as shown. And this would match all topics that start with factory/. Moreover, the hash wildcard can be used to subscribe to receive every message published to the MQTT broker by using it as the only element in the topic hierarchy. Now, as you can probably tell, the simplicity and flexibility of using topic names for data routing, coupled with the fact that they are dynamically created upon publishing, is one of the features that makes MQTT powerful. However, this also means that in a production environment, it's necessary to define a standard topic namespace. This ensures that all devices and applications in your network understand and use the same terms, which enables efficient topic filtering and the effective use of wildcards for applications to access the data they need. Now, the motivation behind creating a standard topic namespace is to really allow you to develop a well thought out topic structure that reflects the semantic hierarchy of your components. This facilitates an intuitive understanding of data representation across your solution. Now that we understand how MQTT topics work, let's move on to understanding the actual payload of an MQTT message. The MQTT protocol does not specify a particular payload structure for its messages. This means the payload can be anything from plain text and formats like JSON or XML to binary data formats like protobuf or avro. Essentially, the payload is treated as an array of bytes. As a result, encoding the message content in MQTT must be managed by the applications or devices involved. It is therefore expected that both the publisher and the subscriber agree on the payload format. For cases requiring easy readability and integration across multiple systems, formats like XML, JSON, or YAML are preferred. On the other hand, when efficiency and reduced bandwidth consumption are critical, binary formats like protobuf and avro are chosen due to their superior compression capabilities. For example, a simple JSON encoded MQTT payload published on the topic of factory/compressor vibration might look like this, where the sensor ID, timestamp, and the actual vibration measurement are required properties. Now, because MQTT is very flexible with how you define the payload, it means that to effectively use MQTT in production environments, it is necessary to define a payload schema for the chosen format. For example, to help a subscriber parse and validate the JSON payload example of our compressor vibration, a corresponding JSON schema could be defined like this. Finally, MQTT supports payloads up to 256 megabytes in size. However, considering the protocol's typical usage in IoT scenarios, payloads are generally small to preserve bandwidth and ensure efficient message delivery. Now that we have an understanding of MQTT PubSub architecture, topic namespace, and payload definitions, I want us to explore the more advanced features of MQTT with the goal to demonstrate how you could effectively leverage these in building a connected solution. Now that we've covered how the PubSub architecture, topics, and payloads work, let's discuss how MQTT ensures reliable messaging in your connected solution. We'll start with quality of service, a mechanism in MQTT for guaranteeing message delivery. Now, when building a connected solution, one of the most important capabilities you would expect from a communication protocol is some form of guarantee of message delivery. Specifically with MQTT, consider if a robotic arm on the factory floor sends a message to the MQTT broker. Does it receive an acknowledgement that the message was received so that it can retransmit the message if it was not successfully delivered? Well, to ensure message delivery, MQTT provides a quality of service mechanism and an inherent capability to handle message retransmission. In order to cater to the different needs of applications and users, MQTT specifically defines 3 different levels of quality of service. Quality of service level 0, 1, and 2. Now, before we dive into how quality of service works in MQTT, it's important to note that the quality of service is a contract between 2 parties, a publishing MQTT client and the broker, or a subscribing MQTT client and the broker. It is not an end-to-end message delivery guarantee from publisher to subscriber. Let's start with quality of service level 0. QoS 0 is the lowest quality of service in MQTT. When an MQTT client publishes a message with QoS 0, it is guaranteed that the message will be delivered at most once. This means the client will not receive nor expect any delivery acknowledgement from the server. If the message fails to reach the broker on the first attempt, the client will not retransmit it. This approach is commonly known as fire and forget. The main benefit of QoS 0 is its minimal latency and bandwidth usage, since there are no additional messages exchanged after publishing. However, there is a risk of message loss. Therefore, QoS 0 is best suited for telemetry monitoring applications where occasional message loss is acceptable because new data is continuously sent. Now let's look at quality of service 1. This level ensures that the message is delivered at least once. For example, if an MQTT client publishes a message to the broker with QoS level 1, it stores the message until it receives an acknowledgement from the server. If the acknowledgement is not received within a certain time frame, the client will retransmit the message. As a result, the broker might receive duplicates of the same message multiple times. However, because duplicate messages can be managed at the application level, QoS 1 is often suitable for connected solutions that require some form of delivery guarantee. It allows you to build a highly reliable solution without sacrificing too much efficiency, as it uses the minimal necessary communication handshakes. Moving on to quality of service level 2, QoS 2 is the highest quality of service level in MQTT. It ensures that each message is received exactly once by the receiver, meaning no message loss and no duplicate deliveries. For example, when an MQTT client publishes a message to the broker with QoS 2, the broker responds with a publish received acknowledgement. This acknowledgement indicates that the broker has received the message but has not yet fully processed it. Upon receiving the publish receive acknowledgement, the publishing client sends a publish release message to the broker, signaling that the broker can proceed with processing the message. After the broker completes processing, it sends a final acknowledgement back to the client using a publish complete message. This multi-step communication handshake introduces significant overhead in terms of latency and bandwidth. However, QoS level 2 is crucial for applications where duplicate message delivery could cause serious issues, such as in financial transaction processing. As a general rule of thumb, avoid using QoS 2 unless it is absolutely critical. The high efficiency cost may not be justified for many applications due to the increased latency and bandwidth usage. Now, as mentioned earlier, quality of service levels in MQTT defines the relationships between a publisher and the broker, as well as between the broker and the subscriber. So in your MQTT solution, different QoS levels can be utilized by various publishers and subscribers based on their specific requirements. Additionally, a message published with one QoS level can be consumed with a different QoS level. Consider a robotic arm operating on a factory floor where network connectivity to a cloud-based broker may be unreliable. The robot can publish its current status data to the broker using QoS level 1 to ensure that messages are reliably delivered. On the other hand, a cloud-based analytics application with a stable connection to the broker might prioritize low latency and high-speed data processing over guaranteed delivery. Therefore, it can subscribe to receive the data from the robotic arm with the QoS level 0. Another important factor to consider when selecting between QoS levels 0, 1, and 2 is the possibility of some components in your MQTT architecture going offline unexpectedly. If you want the broker to queue messages until clients are back online, a process known as store and forward, the clients need to subscribe with either QoS level 1 or QoS level 2, in addition to enabling a persistent session with the broker. What is a persistent session in MQTT and how does it work? Well, let's jump right into it and also discuss how that is related to message queuing within your MQTT network. In MQTT, a session represents the stateful interaction between a client and a broker. By default, these sessions are temporary. When a client disconnects, the broker discards any session information. However, in many connected solutions, you need a more robust solution to handle intermittent connectivity. That's where persistent sessions come into play. By setting the clean session flag to false during connection handshake, a client signals to the broker that it wishes to maintain its session state across disconnects. So, when a client that has established a persistent session with the broker is currently offline, the broker stores messages that are destined for the client using a mechanism called queuing. When the client reconnects, the broker delivers these queued messages, ensuring no critical data is lost during periods of disconnection. Now, as I mentioned earlier, the quality of service levels are integral to how messages are queued and delivered. With QoS 1 and QoS 2, the broker guarantees message delivery even if the client was offline when the message was published. QoS 0, on the other hand, does not offer this guarantee. So as you can see, the combination of persistent sessions and message queuing is powerful for solutions where devices have intermittent connectivity, such as remote sensors or mobile applications. However, you need to be mindful that storing session states and queuing messages consume broker resources. So without proper management, this can lead to performance degradation. So you need to implement strategies like setting reasonable session expiry times and message queue limits. Next, let's explore how you can utilize the MQTT retain message feature when building connected solutions. Now, there is a high chance that in your connected solution, MQTT clients may join at different times. Now, a common challenge arises when a new client subscribes to a topic but has missed earlier messages. So, how can you ensure that this client receives the most recent data without waiting for the next update? This is where you could utilize the MQTT retain message feature. By setting the retain flag to true when publishing a message, the client signals to the broker to store this message as the last known good value for its topic. This retained message is then immediately delivered to any new subscribers of that topic. So each time a retain message is published, the broker updates its retain message store for that topic with the new message and its quality of service level. Now, this feature is really important in scenarios where the most recent state is critical. For instance, devices needing the latest configuration settings upon startup, or dashboards applications that are displaying the current sensor readings. Now, again, this is a powerful feature, but it should be used carefully because overusing retained messages can lead to excessive memory consumption on the broker. Now, the last feature that I want to talk about is the last will. Now, in any connected solution, clients may disconnect unexpectedly due to network issues, power failures, or hardware malfunctions. Such abrupt disconnections can lead to uncertainty about the client status, which might pose challenges for systems that rely on timely and accurate data. To address this challenge, MQTT offers the last will and testament feature, or the last will. This mechanism allows a client to define a will message that the broker will publish on its behalf if the client disconnects unexpectedly. This ensures that Other clients are promptly informed of the disconnection, enabling them to take appropriate actions. Here is how it functions. When an MQTT client connects to a broker, it specifies its last will message, which includes the topic, payload, quality of service, and retain flag. If the client disconnects without proper notification due to, again, a network failure or a crash, the broker detects the loss of connection. It then publishes the last will message to the specified topic, alerting other clients of the client's abrupt disconnection. Thank you for watching. If you enjoyed this video, please leave a like or comment, and of course, don't forget to subscribe.